Hey, good morning, class. Mr. Bean here. I've been asked to do some helpful hints on Lab 15 simulations for AP Physics 2020. And let's see what we got here. This is simulation one. It's called Stopping Distance. Let's take a look at it and see what's going on here. In this problem, you'll be examining a car that is moving along a certain speed and then jamming on the brakes to stop before hitting an object on the road. Okay, and then you'll be given some things about it. Let's see what we got. Okay, so your car is initially moving at 12.5 meters per second when you hit the brakes and your car begins to slow down. So you're decelerating. The car has a mass of 1156 kilograms, and the coefficient of friction between the tires and the road is 0.45. So if you're sliding, this looks like kinetic friction, a coefficient of kinetic friction. What is the time needed to stop the car, and how much ground does it cover during this process? All right, so let me go over here and let's see what we got going on. Drawing here. Let's go ahead and pick black. Okay, so first of all, in this problem here, we have a car. Okay, it's like this here, and we'll call this number one. Okay, um, number one here. And we have a car here going down the road, and there's a road here, and there's some friction here. Okay, so it slams on its brakes. So the motion is in this direction, and the only force acting in the x direction is going to be the force of friction. We have a force of friction that's going to be acting in this direction here. So it's going to be negative. We're going to take going to the right to be positive. So we are given the mass of the car. We're given initial velocity, and we can assume we're on the Earth. So G, we'll go ahead and take to be 9.8, like so. And now that when it comes to rest, or when it comes to stop, the final velocity is going to be 0. Okay, and we're also given the coefficient of friction, mu. Okay, so we're given all this information here. Okay, so in order to solve this problem, we have to first find the acceleration or deceleration. So probably the first step here, we'll call it step one here. So here's, we'll say step one. Okay, and we're going to go sum of the forces. Okay, in the x direction is equal to ma. Okay. Now we should also put on here. We should also note that free body diagram. There is a normal force acting this direction here. There's a normal force here, and we also have the force of gravity mg acting downward. So these are always here, but we're concerned with the x direction, but normal force will play a role in this problem. Let's go back to black here. All right, so sum of the forces equals ma, and the only force acting is friction, but it's got to be negative. So we'll make sure we put negative sign there because this is opposing motion, and it's going to equal ma. Okay. All right, so the left side here is where we have negative mu, and here is mg. Okay, is equal to ma. Okay, remember the force of friction, right, is equal to mu times the normal force. So normal force does make an appearance. Okay, and all right, so from here we see the masses do cancel out. So the acceleration is just going to be negative mu times g is going to be our acceleration. All right, so once we have our acceleration, then we can use our kinematic equations to find out what we need. So we need final velocity is equal to, right, VO, right, plus AT, okay. Now remember, A is going to be negative, so make sure we put a negative in here for A. Even though this is positive, we're going to be putting a negative A in here. And then it says, how far does it cover? Well, we can do two things. We could either use this equation here, delta x, right, is going to equal VOT, right, plus 1 half AT squared, like so. Or we could also use V squared equals VO squared here, plus 2A delta x. Whichever you like, you're free to use either one of these. All right, so that's some hints on how to do simulation number one. Okay, class, we're now going to talk about simulation number two. So here you're given the gravitational field, mass of the car, and when you start, you have to press on the gas to get some starting speed. Okay, and then when you hit the brake line, you're going to slam on your brakes until you come to rest. So in this problem, in my example, what I did was I started, my initial velocity was 15 meters per second. So in my problem, I made my initial velocity be 15 meters per second. I would choose something easy, but I chose 15 meters per second, and my final velocity is going to be zero. Okay, and in this particular case, G is given as 9.95, so it's a little bit different. I'm also given the mass of the car. But in this time, I'm not given the time, so there's no time given. But I do know that I'm going to use the front of my car to measure the starting point and my ending point. So in this particular case, my delta x is going to, yours might be different. So my delta x was like, this is 60, 61, 62, 63, 64, 65, 65.5. So we'll say 65.5 meters. Okay. So we're asked to find the acceleration, uh, and we're also asked to find the force of friction, and we're also asked to find mu. So these are all things that we need to find in this problem. Okay, so take a look here. So we know that the force of friction is going to be mu times Fn. Okay, so we know what that is. This Fn, and we can figure out what mu is. So first of all, what's the acceleration? Okay, so a couple of ways we can do this problem. Um, Okay, so, okay, I have a distance traveled. Okay, I need to find A. So time's not given. So let's start, let's go ahead and say start. And let's start with this equation here. V squared equals VO squared, right? Plus 2A delta X. Now, a is going to be negative. Okay, it's going to have a negative value. Okay, because we're slowing down, and going to the right is positive. Okay, so motion in this direction is positive. Okay, all right. So we know that. So from here, I think I have everything I need. I have my initial velocity. I got my final velocity. 2 is 2, and I have delta x. So from here, we can solve for a, which should be negative. Okay, it should be negative. All right, so I got this here. All right, now I need to, in order to solve for the force of friction, I need to figure out the normal. So there's a normal force. So I need to figure out what the normal force is. So the normal force, okay, is going to be mg. Okay, so there is a normal force, which is mg. Okay, all right. So I need to make sure I do this here. Make sure I got the normal force here. And so I got the acceleration. So let's take a look at the force of friction. Okay, so uh, sum of the forces is equal to ma. All right, so uh, this will be part one. Maybe this will be part two if we need it. And this will be step three. All right, so step three. Okay, so the only force acting here is going to be the force of friction, right? So it's going to be the force of friction. And so we can go ahead and put in here friction. Okay, all right, and we do know the mass, right? And we also know the acceleration. So acceleration, remember, is going to be negative, right? So when I do this problem here, the force of friction is also going to be negative as well. It's going to be negative in here, and here's my force of friction right here. All right. Okay, so there's the force of friction. Okay. All right, so now I have my force of friction. And so step four, if we need to, we know that the force of friction, right, is going to equal mu times the normal force. And I think we already calculated the normal force. Okay, so If you want to, maybe we can use like the absolute value here for this, and we can get that mu is going to equal, right? Uh, the the force of friction, we'll take the absolute value, and we're going to divide it by Fn. All right, and that should be mu. All right, give that a shot and see what we got going on. Okay, class, Mr. Bean here, and let's go ahead and kind of move this out of the way here, and let's see. Uh, all right, simulation 3 here. It says motion on an inclined plane, and go ahead and there's some information about what's going on here, and it wants to know how far will this block go up the incline before it comes to rest. So let's go ahead and click on begin here. And so Newton's law is to find out the distance the block will travel up the incline before it comes to rest. And we're given some information here about the problem here. All right, so first of all, we look at this, we need to know that there's initial velocity given, and the initial velocity is going up the ramp. So going up the ramp is positive. So here's our little model here, and here's our block. So it's going to go up the ramp, and we'll say going up the ramp is going to be positive, and this direction down the ramp we're going to call negative. Okay, that's friction is going to act in the negative direction. All right, so VO is given. Okay, we're also given the mass here, and we're also given the angle theta, and we're also given G, which is a different value than what's on the Earth, and we're also given mu. All right. So as always, the first thing we looks like we need to find is what is the acceleration. So we'll go ahead and call this step S1. Step 1 is what's the acceleration. So we have to go sum of the forces, right, up along the ramp. Okay. So if you need to, you can kind of like draw this, and uh, this is positive in this direction, and this is positive in this direction. So this is like the x-axis, and here's theta right here. All right, so sum of the forces is equal to ma, right? Okay, so the forces we have, okay, so we got to be careful now. As it goes up the ramp, the only forces are acting are going to be there's going to be a force parallel, which is always acting in this direction. So the parallel force always acts in this direction. But since it's moving in this direction, we also have a force of friction that's also acting in this direction as well. Okay, and it's going to be negative. They're opposing motion. Okay, so we could say in here we're going to have the parallel force, right? I'm going to write it like this first: parallel force plus the force of friction, okay, is going to equal ma. Now, gotta be careful now. Watch our signs. So it's going to be minus mg, right? Sine of theta is the parallel force. Sine of theta, all right, minus mu mg cosine of theta, okay, equals ma. All right, now look closely here. Some things cancel out. Looks like the masses do cancel out. So this will be the first step. I need to get acceleration. All right, now that I have acceleration, there's no time given at all anywhere in here, right? So, but I do know the final velocity is going to be 0. So the final velocity is going to be 0. And when it's 0, how much distance did we cover? All right, so the only equation it looks like that might be applicable here, or kinematic equation, is the one that does not have time. So v squared equals VO squared, right, plus 2a, right, delta x. All right, now I got to be careful. This a is going to be negative, okay? And this is going to be 0, and we have initial velocity and 2 and delta x. So it looks like we need to solve for delta x, and that should be the answer there. All right, we'll hit pause. Next one is going to be simulation number 4. It's called net force difficult. And so we are given 3 random forces, and we're asked to figure out the magnitude and direction of the net force. So let's see what we got going on here. So here we have our object here, and we have various forces that are acting at certain angles. In fact, it tells us the magnitude and direction up here. All right, so we can either do it by hand, or I'll go up here and do vector calculator. So vector calculator, and I'll select this one right here. And I like math is fun. All right, so essentially what I'm going to do is da, da, da. Whatever these forces are, here's 48 at 246, 35 at 166, and 55 at 10. So I'm going to look at these forces here, and we're going to use the vector calculator. And I got to be careful about what quadrant is going to be in, because this may, we may have some coterminal angles involved here, and we'll make sure that we are taking it with respect to the positive x-axis. Okay. All right. That's simulation number 4. All right, simulation number 5 says here you'll be presented with an object on an inclined plane with a certain coefficient of friction present. Your job is to determine the normal force on the object at the moment it first starts to slip. All right, looks like something we did in class. Okay, so here it is here. And okay, find the normal force at the angle of the inclination just enough to get the block starting to move. Okay, all right. So find the normal force on the block if the angle of the inclination is just enough to get the block to start moving from rest. The coefficient of friction is 0.68. All right, so it looks like, let's see what we got going on here. So first of all, we have an incline here, and let's see if how we might do this problem here. All right, so we have this here. We have the block right here. Okay, and there's some unknown angle here, so we don't know what this angle is, but we do remember that mu static, right, mu static is equal to the tangent of theta. All right, so what we can do here is that this is mu, and we are given mu, so mu is given. Okay, mu not meow. Mu is given, so we know what mu is. So it looks like I might be able to use this relationship here and figure out that theta, right, is going to be the arctangent. Okay, here's tangent minus 1 of mu. There's the arctangent. That should give me my theta. Okay, now the normal force. So what is the normal force? Let me go ahead and use a different color here. So we have here, this is the normal force. That's the normal force here, right? And we have mg. This is the force of gravity. There's mg, right? There's mg. And we use a different color pen here. Let's use green. All right. So this here is going to be the perpendicular force of gravity, perpendicular force. We're going to go ahead and use this green for gravity. And remember, this here is the force parallel. Okay, so it looks like that F. Okay, so we're in the y direction here, right? This is x, and this here is y. Okay, let me go back to black now. So sum of the forces in the y direction is going to equal 0 because it's not accelerating in the y direction. So that means that up equals down. So up equals down. Only force going up is Fn. Okay, and the perpendicular equals the perpendicular force, and we should have this memorized as mg, right, cosine of theta. All right, so it looks like in this problem here, we have theta from here. So there's our theta, cosine. Make sure we're in degrees, right? G on this planet. So it doesn't tell us anything different. So we know that G is 9.8, and we're also given the mass. And we can assume that G is 9.8. And so the normal force is just going to be mg cosine of theta. All right, hits pause. All right. Hey, class, we're now on simulation number 6, friction to projectile motion. In this program, you will have to determine the horizontal distance traveled by a projectile. The projectile will be a small box that had previously been sliding across a table. The object was subject to friction while it was on the table. Okay, so let's take a quick look here. All right, so looks like this is delta x here. There's mu, and there's initial velocity given. So question is, so this is 8.64. Now, if there's no friction, this would be a simple problem that we would know the launch velocity, it would be 8.64. However, because there's friction and it travels this distance, this is going to slow down considerably. So our task is to find out what is the final velocity here so we can calculate what the projectile, how far is it going to travel in this direction here. All right. And let's see, anything else that's given. We know that this is 198 centimeters. And let's take a look at the question. So here's the question. All right, so let's write down given information. Okay, so the given information is, okay, we are given the mass. Okay, so we are given the mass. Okay, we're given G, gravitational field is a little bit different. Now, this is important here, the vertical distance. So we'll call this here delta y. Delta y is given, vertical distance. It's in millimeters, so make sure we're in meters. Box has initial speed, okay, initial velocity. Okay, so it's given, we're given initial velocity, we're given delta y, G, mass, and we're also given mu, okay, and we also know what delta x is. Delta x is the distance it travels on the table. So delta x on table. Okay, be careful. There's a couple delta x's here, so we're going to say this is on table. So delta x on the table. So we got to be careful. Okay, so it says here, determine the speed of the box at the edge, which is the final velocity. Determine the time in the air. Okay, that's needed to do projectile motion, and determine the horizontal range traveled by the box as it is a projectile. So these three have to be computed sequentially, but all this is predicated on knowing the acceleration. All right, so let's hide the questions here. So here we have our box here. Okay, we'll go like this here, and it is starting right here. So the box is moving. Our goal is to figure out what is the velocity here. So we want to figure out what's the velocity here. Okay, that's what we need to know. In order to do that, we have to first of all know the acceleration, okay, because there's friction involved. Okay, all right. So in order to do that, we'll go ahead and do sum of the forces, right, is equal to ma. Okay, and just to get us a recap here, we do have the normal force acting in this direction here. There's the normal force, free body diagram. We do have mg acting here. And we have a force of friction that's acting in this direction, force of friction. Okay, and this will be negative and this will be positive. All right, so we have in here minus the force of friction, okay, equals ma, right? So from here, we should be able to solve for A. So here's A. A is going to be minus mu mg. Okay, and this is ma, right? So the masses cancel out. So from here, we get our acceleration. Okay, so we have to get our acceleration. So this would be step one. There's our acceleration. Step two is what's the final velocity when it gets to here. So we can probably use v squared, right, equals VO squared, right, plus 2a delta x. Now we are given delta x, and we know what VO is, and we want to find out what V is. And make sure that this is negative, so be careful. That's going to be negative. So that's going to give us our final velocity right here. So from here, we'll get our launch velocity. So this is our launch velocity. I'll say that this is our launch velocity. Okay, launch velocity. All right, so step three, now that we have that in any projectile motion problem, we need flight time. Okay, so we'll say flight time, and flight time is given. Now remember, now when it launches right here, when it launches here, theta is going to be 0, right? Okay, so as we do with any projectile motion problem, we do that. We do the initial velocity x is going to be VO cosine of theta. Okay, so in this case here, the launch velocity is going to be this right here. This is going to be the launch velocity. Okay, all right, and VOY is VO sine of theta, and this VOY should be 0, right? So VOY is 0. So to do flight time, delta y, right, is going to equal VOY t, right, plus 1 half GT squared. Okay, now when we do the vertical motion problem, now brand new thing here, when we do vertical motion, use difference. Okay, in this problem here, we'll take this direction to be positive and this direction here to be negative. This is for the projectile part. Okay, go back over here. All right, so from here, we should be able to solve for t. So this gets us our flight time. And then finally, the fourth step is horizontal range. So we should know that x, okay, horizontal range is going to be the launch velocity times the flight time. So we have our launch velocity from here. Okay, this is our launch velocity, and we also have the flight time, and that should be our range. All right. All right, class, this is number 7 here, and this is the, we'll call this the cougar problem. Okay, this is a cougar, okay, and it looks like he's kind of hungry, so try not to get ravaged by the cougar. All right, so we'll be presented with a block which is moving along an inclined plane. So what's going to happen is that this is its original position. It's going to move up the plane, stop, and then come back to its original spot. Now, if there was no friction, the final velocity would be the same as initial velocity. However, there is friction. So as it moves up the ramp, it's going to lose velocity. It's going to stop and it's going to come down. And it's also going to have lots of friction and it's going to move down the velocity a little bit slower. So the final velocity when it comes back to original position should be considerably less than when it launched up the ramp. So let's take a look at the problem here. All right, so just so we understand what's going to happen, this is going to move like this, pause, and it's going to come back like this to its original spot. So our job is to figure out what's the velocity when it returns back to original position. So this is really a two-step problem. First step problem is to figure out how far up the ramp does it go. Then the next problem is what's the final velocity down the ramp. Okay, so two-step problem here. But first of all, let's go ahead and see what's given in this problem. Okay, so given information. Okay, so we are given we're given initial velocity up the ramp. Okay, let's do this. I'm gonna call this given going up the ramp. Given up, going up the ramp. We have initial velocity, right? And we know the mass, and we're given the angle theta. And we also know G of the planet, okay? And we're also given mu. So all this information is going up the ramp, okay? So we did this problem earlier, okay? So this is going up the ramp here. So in this problem here, what's needed is that we need to know what is delta x going up the ramp, okay? That's what's needed, okay? Now, let's take a look here and make sure we examine all the parameters here. So here's theta, okay? So here is the block here, and the motion is initially up the ramp. So there is a VO that's given, right? All right, so it's going to move, move, move. And the question is, I'll go ahead and put this where it stops here. So here's okay, what is this delta x? That's what we need to know. So here, velocity is going to be 0 when it's up the ramp, right? When it stops. Now, a couple of things here. As it moves up the ramp, we have the parallel force acting in this direction. So there's the parallel force. And we also have the force of friction, which is acting in this direction here. So these two are the only forces acting as it moves up the ramp. Okay, so as usual, we need to figure out what's acceleration. So we'll go ahead and put down here what's A. Okay, that's step number 1. What is acceleration? So we'll do sum of the forces, right, is equal to ma. Okay, so I'll help you out here a little bit. So it's going to be minus the parallel force minus the force of friction is going to equal ma. So this here should get us our acceleration. So there's our acceleration, okay? And then step number 2 is what's delta x, or what's delta x? So what's delta x? Okay, so delta x, since time is not given, v squared equals vo squared plus 2a delta x. So from here, we get delta x. Okay, so this will get us delta x. So now we have delta x. So we have this problem here. So that's going up. That was our goal. What is delta x going up the ramp? All right, so now we'll call this down ramp. Down ramp. Okay, down the ramp. All right, so let's go ahead and draw our situation here and down the ramp. So here we are down the ramp. Okay, and we do know, this time we do know what delta x is. So this is going to move in this direction. Now this problem here, initial velocity is going to be 0, right? And it's going to move to this original spot. This is this original location here. So when it's here, what is v? That is the question. What's v when it comes back here? Now, as it moves down the ramp here, I'm going to use a different colored pin here to figure out what are all the forces that are acting. So as it moves down the ramp here, we have the parallel force, which is acting in this direction, right? There's a parallel force. And we also have the force of friction, which is acting in this direction, force of friction. Okay. And as usual, we need to figure out what's A. Okay. So what's A? Okay. What's A? So sum of the forces, right, is equal to ma. Brand new problem is ma. Okay, so here parallel force is now going to be positive because going down the ramp is positive, going up the ramp is negative in this case. So we have parallel force minus the force of friction, right, is going to equal ma. So from here we should be able to solve for acceleration. Okay, and then finally, what's uh, what's v? So we're going to be using v squared, right, is equal to vo squared plus 2a delta x. Okay. Now, a in this case is going to be positive. Okay. It's going to be positive because it's going down the ramp. It's going to be going faster, faster, faster down the ramp. So a here is going to be a positive value. So be careful. A will be positive. All right. So we'll go ahead and calculate it, and then we should be able to solve for v. All right. All right, class, this is now simulation 8. This is the forced angle problem here. And we're asked to find some things here. We're going to be pulling like on a block here at an angle, like a suitcase, for example. We'll click on begin here and determine the acceleration of the system here. All right, so so let's take a quick look and let's kind of draw this out and see what we got going on. So here we have a block. It could be a suitcase. Okay, there is friction involved. Okay, and we're going to be pulling it at some angle. So we'll call this force here. There's some angle which is being applied at, and we do have friction involved. Okay, so mu is given, and we're going to assume that G is going to be 9.8 because we're not given anything different. And we're also given the mass, and we're also given the angle theta, and we're also given the force, this applied force here. So we're given all this information here. And here's the angle here in which it's being applied at according from the horizontal. All right, so first things first, let's do a free body diagram of all the forces acting in this system. So let's go ahead and go to green here, and we'll use green for vertical. So we do have, as usual, we have the normal force acting in this direction here, right? And we also have mg acting in this direction. Okay, all right, that's it for right now. So let's do different colors. Let's do blue for horizontal. All right, so over here, this is a vector. We have to do this in components. So we do have a horizontal component here, which is going to be f cosine of theta. Okay, and we also have a horizontal component, vertical component in this direction, which would be F uh, uh, sine of theta. All right, we have all this, and then we have one other force. We'll use red for friction. We have a force of friction that's acting in this direction here, force of friction. All right, so we have to analyze this. So we have two dimensions. So we have to consider we'll call it the horizontal and the vertical. Okay. So the horizontal, we have some of the forces, right? And we'll say in the x direction is equal to m. And I'm going to go ahead and draw an A with a subscript x to show the horizontal distance, horizontal motion. So the only forces acting horizontally, now we'll say going to the right is positive. This direction is positive, and going to the left is negative. So it looks like we have this f cosine, f cosine of theta, which is the uh, horizontal component of the applied force, minus the force of friction, okay, equals max. Okay, and let's go ahead and plug in some information here. This is going to be f cosine of theta, right, minus mu mg, all right, is equal to max. Now let me go back and rewrite this again a little bit. Let's go let's go ahead and do cosine of theta minus mu. Let's just do Fn here. Let me just rewrite it as Fn is equal to max. All right, so this is what we want to find, this right here. Okay, that's our goal. Now the vertical, okay, so the vertical, rewrite it over here, vertical. Okay, so we're going to have some of the forces in the y direction is going to equal 0 because it's not accelerating in the y direction. So this implies that up equals down. Okay, so only forces going up are the normal forces going up, right? And we also have this F, looks like sine of theta, is equal to mg. Okay, so the normal force here, right, here's the normal force, is going to be mg minus F sine of theta. All right, so that means the normal force, if this was a scale, it would be less because there's an extra force going upwards, which would make a scale reading less. All right, so here's our normal force. So here's the trick. I'll put this in parentheses here. This normal force has to go right here. So once I plug that in there, then I can quickly solve for A. And that's what we want to try to find in this problem. All right, we'll go ahead and hit pause.